Hi everyone and welcome back to the DIY amplifier kit. So today I'm not gonna actually start building. I'm going to talk a little bit about in more detail about some issues that I have encountered here with this kit, and there are some things here that are a bit problematic, and we'll go through that and talk a little bit. And I'll also talk about some other things in this video, such as issues with obtaining parts for electronic projects right now. So, yeah, I was going to build this amplifier, and it's really nice. For the price of this, it's absolutely incredible what you get. These output transformers and power transformer is worth way more than the whole kit on its own, which is absolutely incredible. The deal you get here, two really nice output transformers, a very nice power transformer, you get a lot of usable parts, and you get this actually quite nice chassis, and you get all the tubes. Absolutely incredible, but there are a few issues here. But the first thing I'm going to talk about, which isn't really a huge deal, but it is something that we are going to talk about, that's this circuit board here. So the circuit board for the actual amp circuit is really nicely laid out. You can see it's got star grounding and all that. Really nicely laid out. There's nothing wrong with that, but there is a bit of a quirk here. So if you flip this thing over, this is the component side, and we've got a few issues here. So we have the 6.3 volt winding, which is supposed to go there. That's for the heaters and the vacuum tubes, of course. So that goes, let's see if I can grab something to point with. That goes here, and it goes here, and that goes to the heater pins 4 and 5. 4 and 5 on the first output power tube here. But you notice it doesn't continue on to the next tube. So what you have to do is you have to bridge these gaps here to here, here to here, here to here, here to here, and so on and so on and so on. And that's a bit of an annoyance more than anything. There is enough space here. They could have rerouted this a little bit, stuff like that. They could have fit the wire, but they didn't do that. And I guess it's understandable because the current is pretty high in the heater chain. It's going to be about 4 amps total. So yeah, but this wire they included here, the blue one, is perfectly usable for wiring up the filament. It's more than thick enough. And this seems to be solid core. I think it's going to work absolutely fine for wiring up the heaters. However, I would not use this for wiring up the mains voltage side of things. I would grab some proper wire, you know, this sort of stuff, proper 750 volt rated wire. I have a lot of it that's used for building industrial control cabinets and stuff like that. So that's a bit of an annoyance with the circuit board. But other than that, I think it's pretty well laid out. There are a few other quirks here with the circuit board. For example, you may notice there's nowhere to mount your main electrolytics or your rectifier. So those have to go somewhere else. And there is a bit of a problem. If we flip this chassis around, we notice there isn't a whole lot of space here. So this is where the output transformers go. This is where the terminals for your speakers go. This is where your audio input goes. This is where the IEC inlet goes, and this is where you have your power transformer. And everywhere here there's going to be something taking up space. There's going to be the circuit board here, which is going to take up about that much space. There is nowhere to put the bloody filter capacitors in this chassis. So they screwed up there. And that's another thing I want to talk about. These filter caps here. And now we're getting into the other part of this video where I'm gonna talk about some issues. So these caps are pulled from Junk Electronics, and these are genuine Nippon Chemical, most likely, and that's good. They're good capacitors, but unfortunately one of them has been badly dented here, or well, maybe not badly, however it is dented, and when a capacitor gets dented like this, there could be damage to the dielectric inside, which means this capacitor could fail, short circuit, and since this is high voltage 450 volt rated cap, it's not gonna see that much. It's gonna see about 300 or so, but still that's not really good. Now I've tested these caps. I haven't put high voltage to them, but I did, just for the heck of it, apply my multimeter to these. The capacitance is bang on, and there doesn't seem to be any obvious issues with them. However, this of course is not good. This capacitor, I don't want to trust these caps, and there is nowhere to mount them on this board anyways, so these capacitors are not really usable. They are 330 microfarad. However, I don't think 330 microfarads is necessary. It's actually quite an overkill amount of capacitance, I think, which is good because the amplifier is going to be very silent, no hum. But yeah, these capacitors are, well, one of them is usable, but unfortunately I don't want to mix capacitors with other ones. So, and there's a bit of a problem here. I don't have any suitable capacitors laying around. I've looked all through my parts. I don't have anything. I have a lot of capacitors that have similar capacitance but way too low voltage rating, just unusable. So I went to the parts supply, checked if they have anything. They don't seem to have anything in stock right now. There doesn't seem to be anything available, and the few caps that are available, they are insanely expensive. So then I went to the store which sells stuff for guitar amplifiers, and they do have JJ multi-section caps, but they are very expensive as well. But the more annoying thing is they don't have values anywhere close to where I need. They have some capacitors which are single section. One was 200 microfarad and one was 500, but they are just way too physically large, and I can't fit them underneath here. There's just no way. I'm not even going to be able to fit these underneath here. So I've been thinking a little bit, what am I going to do? Well, I have this. This is a Rifa capacitor made here in Sweden, very good quality. But there's a slight problem with this. 300 volts rated, continuous. 300 volts. This capacitor was made in 1965, but it is absolutely perfect. This is a very nice capacitor, nothing wrong with it whatsoever. It contains nasty PCB oil though, but that's not really a big issue because, well, it's not going to physically leak or anything. So yeah, this capacitor, I do have this capacitor, but there is a slight physical problem. If I were to mount this here on the chassis like this, there's a bit of a problem. This is where the IEC input is going to go, the jack here. And if I put that in here, you know, if you just line it up like this, so it's roughly where it's supposed to be, and if I try and put this here, see how close that's gonna be. And of course it's just gonna be the terminal sticking through here, but they're going to be dangerously close to that IEC inlet. And the power transformer here has these brackets on it, these metal brackets here. So it's going to need this space here. So this capacitor must go about here. You can't put it here because it's gonna hit the input jack. We're not gonna have enough space. So we can either put it here or here, and here is not an option because it's gonna be too close to the output transformer. So here is the only option we have, and I am not a fan of how close to the jack that's going to be. That's just outside of my comfort zone. It's not good. I don't like that. Even if we put heat shrink and everything on this, which I am going to, of course. No, I don't want this. This is a very, very bad layout. And there is just nowhere else I could put this. I can't put it here because it's gonna look stupid, and can't fit it underneath. And these capacitors, same problem with these. There's nowhere to bloody fit them, and yeah, it's just a bit of a chaos, really. So I've been thinking about this, but yeah, the problem is there's no capacitors that are rated for greater than about, I don't know, 100 volts available right now. There's just nothing. A lot of them are used for making, switch mode power supplies and stuff, and that market is huge. So there's just nothing left. And yeah, the problem is these are too bloody large. I can't fit these capacitors anywhere in here, because here we're gonna have the output jacks, not gonna fit there, and the circuit board is gonna take up this much space. It's not gonna work. There's nowhere to fit these bloody things. The only space we have is this tiny little place here, and I'm gonna have to drill holes here, punch holes here, but it's gonna be dangerously close to this bloody thing, the input jack, and I can't even use these capacitors because they are dented and I don't trust them. So we have a bit of a dilemma. I don't have any filter caps for this bloody thing. And what's worse is there's a dropping resistor between the two filter caps, a pi filter, and where am I going to mount that bloody dropping resistor? It's huge. It's a 25 watt power resistor. Do you see where the problem is here? Yeah, I could fit it here or something like that. That would probably work, but it's just not ideal. And so yeah, I have some of this board here. Unfortunately, it's got a bunch of holes in it, so this is a bad example, but maybe we can make a rectifier and filter cap board and put somewhere in here. Something like this. Maybe use the screws on the transformers for mounting that. I don't know. But then we're going to need some much smaller capacitors. And yeah, this is the problem. There's not enough space. And that's another problem there, the rectifier. So you get the rectifier here, right? Very nice little bridge rectifier, nothing wrong with this. But there is nowhere to mount the bloody thing. There is no place on this board. There is no place. There's nowhere to mount it. And it didn't include any small PCB or anything for the rectifier and capacitors. So there's a bit of a problem here. We are very space limited, and we must fit our main filter capacitors somewhere, and these are not usable. And even if they were, these would be a slightly better fit here than this, but since these are not usable, this is the best I have, and it's 100 microfarads at 300 volts. So we're going to have to drop the B plus a bit on this amp, which is not something I'm a fan of because I'm going to lose output power. But what can we do? I can go on eBay and buy capacitors, but I'm going to have to wait 3 to 4 months to get them. And I want to build this, you know, during my free time now, not in 4 or 5 months, because in 4 or 5 months I might want to do something completely different. So there's this problem here. There's no parts available. So yeah, here we are. We have this capacitor from 1965, and this is the best I've got. And I am tempted to just try and get this in here and use it. This thing is absolutely fine electrically. It's perfect. No leakage, no nothing. Good ESR. Bang on, it's what it's supposed to be in value. Very, very nice capacitor made by Rifa. Really, really good capacitors. And this was pulled from a working but radio, but that radio had problems with the IF section that I just couldn't fix. It was just too far gone, so I partied it out and I saved this capacitor because it's absolutely beautiful. I also have a lot of other interesting capacitors here. We have some really old Metalmite capacitors here. These contain PCB oil as well. This thing does too, but this thing here is probably never going to leak or anything, so it's not going to be a problem. But yeah, these are quite interesting capacitors. Metalmite Tropics, these are coupling capacitors, paper in oil, in Visconol X oil, which is PCB oil actually. So these are kind of nasty, but yeah, and all of these are, some of them are in really good shape electrically, and some of them are just so gone, it's absolutely unbelievable. Here are some of the worst ones just laying about here. But yeah, I don't have any suitable electrolytics for these. Those things there are too small value wise and they're too big physically. I don't have anything in there. I don't have anything in there. I don't have anything that's usable. This is the best I've got. And I might have to use this thing. And yeah, there's nothing wrong with this cap, but the values are too small, including the voltage rating, so that is a bit of a problem, definitely. So yeah, we're at a bit of a problem stage right now. Oh boy. This kit is... Now when I look at this more closely, I'm realizing it's not all that thought out when it comes to the power supply section. You gotta fit... Where are we even supposed to put these without drilling holes? And there are no holders in the kit, so you'll have to buy those somewhere else. It's just a big chaos. With this capacitor at least, I could just drill a hole, drill holes for these, bend them over, and it would be secure in there. I can't solder to a stainless steel chassis, so it's just gonna have to be mechanically secured and grounded with a grounding wire running over to the circuit to prevent issues. But yeah, I am actually leaning towards this, and yeah, it's crazy. But yeah, the board, I like it. It's well laid out other than the heater stuff, but oh well. I can understand why they did it the way they did though. And it's fine, since there's gonna be quite a bit of current there. I think the parts layout is alright, and I like the silk screening. It's easy to read, easy to work with. You got the tube socket side here, the 6P1. Now be careful with the 6P1s, they are not the same as an EL84 like I initially thought. The pinout is completely different, so be very careful. I was confused when looking at this because I'm used to the EL84 and pin number 7 being the anode. Then I look here, pin number 7 doesn't go anywhere. So I was like, what the hell? But then I discovered pin number 1 is the anode on 6P1. So that goes here over to this, which then goes to a 10 ohm resistor. So all of the anodes seem to go through a 10 ohm resistor. And the reason it does that is so you can actually measure how much plate current you have on the tubes, which is neat, but I would have liked to see that on the cathode instead, because cathode current is really what you should look at to see the total current in your tube. But yeah, they put it on the anode, and that's fine. So it goes here, and then these here, the P and the plus and the P1, this is for your output transformer. So P1 and P2, they go to the outer legs of the output transformer, and this goes to the center tap, of course, and the same over here. So you have the anode from this tube going to the 10 ohm resistor here, over to here. Then you have the anode on this tube on the other side of the board here, going here through the 10 ohm resistor here, then going out to the other side of that output transformer. So it's a push-pull amp, of course. That's how you can get the very high output power that this amplifier delivers. You should be able to get 12 to 14 watts per channel output out of this. You can probably get more if you increase your B plus and do a few tweaks to this. So that's that. And here you got the grid resistors, the grid stoppers, or actually I think it's called grid lake resistors, and they basically go to ground, and they basically prevent stuff like oscillations from happening. So that's those, they go to ground basically. And here is the coupling capacitors from the phase inverter here. So one comes from the cathode, I don't know which one is which here, but one comes from the cathode, goes over to the grid of one tube, one comes from the anode, goes through the cap into the grid of the other tube. So it goes one from the cathode of the triode section, one from the anode of the triode section. It's called a cathode. We can look at it over here. This is the phase inverter stage. This is called a cathodine phase inverter because you're using the cathode as one of them. So this is biased in the center point to give you a equal swing here. So they're opposite polarity. So this here goes, I think this actually goes negative, and the cathode goes positive, and then it goes into the control grid via the coupling caps, and you have a grid leak here going to ground here. This is your common ground point, and this is the bias resistor for this pair of output tube. This floats the cathode up from ground, so that's how you bias these tubes, because the control grids need to be at a negative level, otherwise the tubes will burn out. If you don't have any sort of control over the current flow there, the tube will conduct extremely heavily and it will burn up, red plate, and just die. So they float the cathode up like this, very very common. This is what all medium powered amplifiers do because it's the easiest and it's very effective. It works really really well, especially when you put a capacitor, a large value like this across this. You don't get a lot of voltage fluctuation here when you play bass notes, so you actually get quite consistent power with this setup here. It works really well, and there's no reason to overcomplicate the bias on an amplifier in this power range. If you were working with, let's say, KT66s or KT88s or 6L6s, EL34s, that sort of thing, you might want to consider something called negative grid bias, which is actually a second power supply which is negative, so it has the positive grounded, and then the negative goes up to the control grids, and that controls the bias of the tubes, because the control grids on these small tubes or medium power tubes, you need to control it by making it negative. There are some tubes that can operate without any bias, self-biased tubes such as the 811A or other tubes like that, but then we're getting into RF tubes and stuff, which we're not really all that interested in because they're difficult to work with. They need extremely high plate voltages and can be extremely dangerous to work with for beginners. But yeah, here we float the cathode up, which means that the control grid sees a negative voltage. Even though there is no voltage applied to it, it is going to be above ground level, negative. So it's going to appear as a negative voltage on the control grid. I don't really know how to explain it any better, but that's how this sort of biasing arrangement works. And it works surprisingly well. So there you go. And you can see the screen grids here, pin number 2, they go through some 300 ohm resistors to through a dropping resistor here down to the B plus of the amplifier. So we have holding this camera gets really hard on the hand after a while. So it goes here like that. So in some amplifiers you have tappings on the primary or the output transformer that go here. That's called an ultra-linear setup, and that is actually very good because that minimizes distortion quite a bit actually. Now this here is not bad either. This is also a really good setup, especially when you have good output transformers. This amplifier is probably going to perform quite well with very low distortion as well, but having those tappings there can allow for even lower distortion numbers, but making such a transformer is more expensive because then the transformer needs to have a little bit of a different design. So yeah, that's the 6P1 power tubes. Here we have the 6F2, which is a tube that contains two different sections. One is a pentode section. A pentode has the screen grid, same as these ones. You see pin number 2 here. That's the screen grid. So they can actually operate a whole lot differently from a simple triode tube like this, because you can actually control the electron flow in a different way with these tubes. So the screen grid can help to make the tube a lot more linear than a triode. So yeah, you have the cathode of course here going to a capacitor ground. So we're using the same biasing method here with these tubes. You have the control grid here, which is the input. It goes via a grid stopper here through a grid leak resistor, and here is your potentiometer, and this is your audio input. So that goes there. Then you have the anode here on pin number 6, which goes here, and it goes into the control grid of this, which is the triode section inside of the 6F2, inside the same tube. And this is what they use for the phase inverters. We already talked about that, and I kind of started randomly in the middle here, but it doesn't really matter. So then it goes here, and there's this is the anode resistor here, and this goes to the power supply rail, but it goes through a lot of different stages. Here there's another filter cap here, then there's a 20k resistor here and another filter cap. And the reason there's so many pi filters is because you want minimal hum on this line here, because if there's hum here, it's going to get amplified here, it's going to get slightly amplified here, so you're going to get a lot of hum on the output here. It's going to be very irritating to listen to. And with a solid state rectifier like this, they do actually produce more ripple than a vacuum tube rectifier, so that's why I would have preferred to have the proper value filter caps here, but that's not possible unfortunately right now. Here you have a Sobel network, I think it's called. There's a small capacitor in series with a resistor, and the resistor prevents the tube from driving a short circuit at very high frequencies here, because the capacitor will act like a short circuit to really high frequencies. So this can roll off your treble if this filter is not done correctly. If you have too large of a capacitor here, too small of a resistor here, you can get your treble cut way off. Now most vacuum tube amplifiers, due to the output transformer, cannot reproduce higher than, let's say, 15,000 Hertz, but that's more than good enough actually, because our hearing isn't actually that good anyways. So some designers make sure that no higher than 15,000 Hertz can pass through, and that's fine. That's one way to make an amplifier less prone to oscillation, so it's fine. So that's what that does right there, and yeah, quite simple actually. This here is a suppressor grid. This is the screen grid here, so you can see it goes here to this very well filtered line. So it's the same deal here. You have 300k resistor here going there into there. What else? We had the pi filter here, that's the main filter caps. Then you have another pi filter here, another pi filter here. So there's a lot of, since this is the most sensitive stage, you need the most filtering here. So that's why they've done that. And here you have the slightly less filtered for the phase inverter, and of course this is the power tube, so they draw a lot of power, a lot of current needs to flow here, so of course they have the less amount of filtering. And since these are the less sensitive tubes, there is not going to be any real problem with hum here, so you can run a relatively unfiltered supply with just minimal filter capacitor to the output stage. And that's that. And here you have the output transformer here. Now, no, it is actually here. This is the feedback line here, which goes to the cathode of this tube. If you get this hooked up wrong, you get the phasing of this transformer wrong. If you connect this side of the coil here, for example, or vice versa, the phasing will be wrong, so this will go here, and then you're actually going to get positive feedback instead, which is going to send the amplifier into extreme oscillation. And if that happens, you're going to notice it. Your speakers are going to go crazy. It's going to squeal maybe. It's going to produce, your subwoofer's cone is going to just go crazy. So you're going to notice it if that happens. So what you need to do then is just swap these two, the outer leads, around, and that's going to take care of that problem. So it goes here via this 10k resistor and into the cathode of the preamplifier tube section here. Now in some designs you see a capacitor across this, and that's to give it a different frequency response on the feedback, but this is a pretty neutral setup here. It's going to give it a little bit of feedback. It's going to cut down the distortion considerably, which is always a good thing. And yeah, you got the ground here, which is also grounded to chassis, the 0 ohm or the common, grounded to chassis here of course as well. And you connect your speaker to either the 4 or the 8 ohm tap, depending on what speaker you want to drive. And of course you don't have to connect a 4 ohm speaker here. You could run a 3 ohm speaker or a 6 ohm speaker. You just connect to whichever tap gives you the best performance. So if the 8 ohm tap gets louder, well, use the 8 ohm tap. If the 4 ohm tap works better, well, use it. No big deal. It just impedance matches your speaker to the output tube, because the output tubes can't drive high currents, of course. So the transformer steps the high voltage here, low current, down to low voltage but very high current for driving your loudspeaker. So here on this side you might have, let's say, 40 milliamps per tube here, but on this side here you can have 2 amps, maybe even 3 amps of current going into your loudspeaker. So it's quite a difference actually. It's quite cool. And it works quite simple. And here's the power transformer. You can wire it for either 110 or 220 volts. So here's the 110 wiring. Here's the 220 or 230 winding. And you can see the secondary here is 230 volts. There's no center tap on this, so you can't use a full wave vacuum tube rectifier even if you wanted to, because you need a center tap for that. You can technically use a halfway rectifier, vacuum tube one, if you wanted, if you didn't want to use the solid state. Now I think I am going to use the solid state rectifier because the heater winding here is 4 amps and the current through the tubes is going to be right around there, so I don't want to risk overloading it because that could overheat the transformer and burn it up. So yeah, solid state rectifier hits the main filter cap. You have this 75 ohm resistor. This is a pi network going into the second filter capacitor, and that's it. Now, since I will most likely have to use this, which is only 300 volt rated, I'm gonna have to put some kind of dropping resistor right here in this line to prevent these capacitors from seeing too high voltage. It's also going to reduce the whole voltage for the whole circuit slightly. But if you take 230 volts and do the maths, you're going to get 325-ish volts RMS, or peak, I mean, sorry, peak. And you're going to get about 325 out of this rectifier here. You're never going to be able to get any higher, because that's the maximum. And once you put a load on this, it's most likely going to drop. So I don't know, we might not even overvolt this. And if this capacitor sees 310 volts, let's say, or 315, it's probably not going to care, because these ratings here, 300 volts, that's plus minus 10%. So that capacitor is probably going to be fine as is, to be honest with you. Sounds crazy, but these old electrolytics are really tough compared to modern ones. If you overvolt a modern one just a little bit, it can explode. But these bloody things, they usually don't give a shit, so might be just fine. There's a bit of a thing here I want to talk about briefly. The fuse here, 2 amps, way too much. Should not be needed. Put a 1 amp here if you're going to use it on 220 volts, and use the 2 amp if you're going to use it on 110. Now I think that's way too much, even on 110. You could put a slow blow, probably 1 amp, and you'll still be fine. Try and put the lowest value you can here, without running it right at the limit, of course, because that can really stress the fuse. But, you know, get a fuse that's within 200 milliamps or 300 milliamps of the transformer, and make sure it's I will go with a slow blow for something like this, and so it can handle the startup current, because it's going to be a large surge when you charge up the filter caps here. So slow blow, but I don't think 2 amps is necessary, it's too large, so just put a smaller one there, and you'll be able to save the transformer should something short out in the amp. Let's say your heater wire short out for whatever reason, it's going to pop that fuse and the transformer is going to survive. So you gotta be a little bit careful about stuff like that. But yeah, that's that. Now I've actually been talking for 40 minutes about I've been rambling about the circuit, I've been rambling about the parts problem. I didn't even mean to go through the circuit, but here I am, I just did it, so whatever. If you don't want to watch this part of the video or whatever, well, feel free to skip it. It's not gonna matter. I'm not gonna get offended if you skip parts of my videos, it doesn't matter. But yeah, I want to start to build this soon, and yeah, I think I'm gonna use the circuit board, even though I wanted to build this point to point. there seems to be extreme inflation going on even on stuff like that. So I had a look at how much it would cost for me to buy terminal strips and stuff to build this port. It would be like easily over 60-70 euros just for terminal strips, and that's just ridiculous. So as much as I love point-to-point construction, I don't think I'm going to do it in this case. I'll give the circuit board a shot. We'll see how it goes. And you know, I'm not a big fan of circuit boards when it comes to vacuum tubes because they get hot, of course. These solder joints are going to be under a lot of stress with the heating and cooling of the vacuum tubes. And I do actually believe that they are going to crack. Also, another thing here, if you take one of these sockets out here, I already had a look at this a little bit earlier today. If we take one of these sockets and we put it in here, just so I can show you this, I'm not actually gonna put it in properly, but let's just put it in like that. This here in the middle here, that's supposed to be a structural integral, what's it called? I don't know, whatever. That's actually structural to the tube socket. They cut the hole out here. What they should have done is they should have left this, and they should have left a nice big ring here that we can solder this tab to, because that way when you pull tubes in and out, you're not going to stress the small connections alone. You're actually going to stress the point there in the middle instead, which is going to be much better for the longevity of this, I think. So yeah, I do sadly think circuit boards and vacuum tubes don't work too well together, simply because of the heat output. And I do believe we could actually get some cracking in the solder joints. Now when I solder, I use lead solder, I use proper solder. This is 6040. This is kind of thin though, I want to buy some thicker stuff, but this solder is not very prone to actually cracking. So, because it gets really good strength, and it is actually slightly flexible. So I think lead solder is the best when it comes to any kind of electronics. Lead-free solder is cool and all, but it is really not all that great. I find that it just doesn't make as good solder joints, and you have to use a lot more heat than you really should, and that's of course not good either, not when working on circuit boards. Yeah, I don't like it, and it also eats the tips like crazy. And this tip here is many years old, and because I've only used it with leaded solder, it is still absolutely fine to this day. So yeah, it does actually make a large difference, solder. It may not seem like it, but it really does. It makes a huge difference. Yeah, it's been 40 minutes. If anybody is still watching this long into the video, I'm actually impressed. Yeah, also, here are the wood pieces that go on the side, and I have to say, these are actually really nice. They are very nice, in fact. And they go like this on the finished amplifier. Very nice. I'm actually going to put these away so that I don't scratch them up and destroy them. So we're going to put those away somewhere here or something like that so we don't damage them. But yeah, that's where we are. We have a few issues. Capacitors and space issues and general problems. And yeah, the capacitor shortage and stuff is really irritating, because I'm sure I'm not the only one who needs capacitors right now, and there just doesn't seem to be anything available. But yeah, I'm really glad that you get what you do here in the kit. You get fairly good stuff, and you get this is a shielded audio cable for the signal side of things, which is also really nice. I do actually have some better stuff than this though laying around, which I could use if I wanted to. But I think the binding posts and everything is actually really good stuff. This is definitely up to my standards, and I'm pretty satisfied with all that. Yeah, there are a few things in here I don't like yeah, we already talked about that. Oh yeah, there we go. Amplifier project being a bit of a struggle, and the water pump has started, so I think it's time to round up this video. Oh yeah, there you go. Physical issues, as always. But yeah, I think we're gonna be able to actually make this happen. I don't think that we are at any sort of impossible stage right now. We're gonna be able to make this happen, but it's going to take a bit more time. And I don't know what I'll do about this capacitor problem. I might actually just try this, and if it works, it works. If it doesn't, well, whatever. But I would like to get some new capacitors, and we would have to figure out some place to mount them. I think we're just gonna have to drill holes here and live with the fact that there's almost not gonna be any space left. So yeah, and this thing here, if you put it to this side, I think it would actually work, and it would look quite good on here as well, being a nice polished aluminum can in really good shape. But yeah, that's it. Thank you for watching, and I think I'm gonna go inside because it's getting quite late, to be honest. But yeah, we had a bit of a look at this at least, and yeah, a lot of issues, definitely. But I think we're gonna be able to make this happen. I definitely don't think it's gonna be impossible at all, but because of the issues with the power supply section here, I'm gonna have to think a little bit about what I do here, because if I drill a hole for this in the chassis, it's gonna be a permanent thing, and I'm gonna have to just live with it. So we'll see what I do. See you later.